We're starting our unit on kinetic molecular theory. And this is a theory about how molecules move and the energy. So if you're moving more, you have more energy or more energetic. If you're not moving a lot, you have less energy. And the energy we're talking about is kinetic energy, and that is the energy from motion. And so to understand this, I like you guys to think about water. Water is a perfect molecule to understand what's going on here. Okay, so we're going to talk about 3 states of matter. There's many more, but right now we're talking about solids, liquids, gases. Over here, if we kept going, more energy, we'd have plasma. Less energy, we'd have a Bose-Einstein condensate. But again, we're just talking about solids, liquids, and gases. So if I look at water and it's a solid, it would be an ice cube. So it would be a nice, regular, patterned molecule, very tightly packed. Okay? Now, if I add some energy to that ice, those molecules would start moving a little faster and they would melt and they would start slipping by each other. So right now, a lot of you guys might say a solid has no motion, but a solid is always moving. So the motion in our solid is just vibrational motion. Okay, it's our solid. Here's our motion. Vibration. Liquid, it's slipping by. And that's why liquids are pourable, because those molecules can run right past each other and they just slip on by. And then we have our gases, and they are no longer touching. This is important. Our solids are touching, our liquids are touching, and our gases have so much energy that they can free themselves from those attractions. So let's refresh what our intermolecular forces are. Those are the forces of attraction between molecules. They're not bonds. So you can think of all these molecules as having Velcro on them. And the stronger the Velcro, the stronger the force of attraction, the more they stick together. Okay, so here I have very low intermolecular forces. These have a lot of energy, so they're flying by. They're just crazy, moving, bouncing all over the place. Okay? So what happens is I'm going from a solid to a liquid to a gas. As I go this way, we're gaining energy, gaining kinetic energy. Okay? And if I go from a gas to a liquid to a solid, we're losing energy. Okay, so gas to liquid to solid, we're losing energy, spelled correctly now. So when we look at our kinetic energy and we compare this, we have the lowest energy, lowest, to our gases, which has the greatest kinetic energy. Okay? And now we're going to talk about density. Remember, density is mass divided by volume. I like to make my little heart here, and if you cut it in half, we have mass divided by volume. So how much stuff is in the same amount of space? Well, solids, they're packed really tightly, so there are a lot more particles I can put in the same exact space. So this is very dense. And then if I go over to gases, there's not very many particles in this same amount. So this is least dense. And now I want to talk about compressibility. So here I have an example of a solid. It's in a syringe and it has a certain amount of volume. Now, can I compress this solid? I can push this down as much as I try and I can't compress it. My volume stays the same. Okay, why? Because there's hardly any space between those particles. Now, for a liquid, there looks like when we draw it a little bit more space because they're slipping by, but in actuality, there's not. So in here, I have a liquid. Okay, and I'm going to just put my finger here so it doesn't leave, but you can see I cannot compress this water. I'm pushing as hard as I can and my volume is not changing. So liquids are not compressible at all. Compressible, no for solid, no for liquid. And then I have gas, okay? So I'm just pulling up, putting some air in here. I'm gonna put my finger here again so nothing can come out. And you can see, let's put this exactly at 10. There's my 10, okay? Now I'm gonna push as hard as I can and watch how much I can press that gas. I can compress it a lot. So gas is very compressible. Why? Because there's a lot of space between those particles, so I can squeeze them together. And you guys actually know this because you may have used helium balloons. And you fill that up from a tank. That tank is a compressed gas. So that helium tank that you get that looks like it takes the space of maybe 4 or 5 balloons can actually fill up about 500 because the gas is compressed. So when I put it in the balloon, it starts spreading out and we have more volume. Okay, so solids cannot compress. Liquids, although they can move around now, there's still hardly any space, so I can't compress them. Lots of space there. Intermolecular forces of attraction. So how tightly are those particles attracted to each other? And our solids, they're touching, so the intermolecular forces are very high. Okay? In liquids, they can start moving more, okay? So they can slip by. They can do that because we've added energy, and the motion can make that Velcro loose and they can start moving, okay? So high, and then our gases, they're not even touching. So our intermolecular forces are none, okay? High, lower, to none. And remember, we want to think about that as our stickiness or the amount of Velcro. And then here is what I really dislike that they ask all the time: shape and volume. And what they're asking about is it changeable? So if it's a definite shape and a definite volume, that means it doesn't change. So here's our solid, and think of that ice cube. And don't think about it if it's melted. Think about if it's frozen, it's staying cold. The shape is definite. And the volume, so if I have an ice cube that is a 2 inch by 2 inch cube, that's the volume, 2 by 2 by 2. And so it doesn't change, okay? Remember, this is all at the same temperature. So now we want to talk about the volume of water. So here I have roughly 9 milliliters of water. If I move that water into this little tray, do I still have 10 milliliters? I do still have 10 milliliters. So liquids have a definite volume. That volume did not change. Okay, but when it was in here, it was shaped like a long tube, and now it's shaped like a flat disc. So my shape is changeable, and we call that indefinite. Now, you saw me change the volume of this gas, right? So I have 10 milliliters and now I have 5 milliliters. So the volume of gas is changeable. We call that indefinite. And notice the shape also changes, right? It was a long tube and now it's a shorter tube. So I have a changeable shape as well. So you can remember this by solids have a definite shape and a definite volume. Gases have a changeable indefinite shape and a changeable indefinite volume. And liquids have a definite volume. It doesn't matter if I take that gallon of milk and pour it on the floor, it's still a gallon, but the shape has changed, so that's indefinite. So now we've learned about solid, liquids, and gases, and if I add energy, I can change the states of matter, which is also called a phase change. So a phase change or a state change is the same thing. It's important to know, and this will be a question, is this a chemical change or a physical change? Remember, I want you to think about water. A chemical change is when I make a completely new substance. If I have a solid water, which is ice, liquid water, or gas water, which is humidity, is it still all water? It is still water, and that's why it's a physical change, not a chemical change. And now we're just going to name what happens. So if I take a solid, I add some energy, it'll start moving more and turn into a liquid. So remember, think about ice. If I have solid water and it goes to a liquid water, what happened to it? It melted. So this phase change is called melting. Now if I take that liquid and I remove some energy, okay, and it slows down and it forms into a solid, what happens? So if I have liquid water goes to solid water, I froze. So that's freezing. Freezing. Okay. Now, we have liquid water and we are going to go to a gas. So it's turning from a liquid to what I like to call a vapor, and that's called a vaporization. Okay, so when we go from a liquid to a gas, it's vaporization. Now there's two kinds of vaporization. There is boiling, where we make the vapor pressure equal or greater than the atmospheric pressure, so that's boiling. But then we also have those puddles that evaporate on the street. Well, they're certainly not boiling, they're evaporating. So we'll add that in a second. There's two kinds. And then we have a gas going to a liquid. So what I want you to think about is that cold glass that you have, and you bring it out and you sit out by a pool and it's really hot outside. So what happens on the outside of that glass? You have little drops of water forming on that ice cold glass of water if you bring it outside on a hot day, because that water condensed. So that's condensation. Or sometimes you see condensation on your windows in the morning. And what happened was it cooled at night and there's humidity in the air, but it got so cold some of that humidity or some of that gas, water gas, slowed down and condensed back into a liquid, and that's what those drops of water are on your car windshield in the morning sometimes. Okay, now going from a solid to a gas is a word you may have heard of. It's sublimation. And this is, sublimation, and this is how, if you go to a concert and there's fog on the stage, they just take dry ice. And they do that because that ice goes from a solid right to a gas with no liquid. And that gas looks like fog, but then there's no water or, stuff they have to clean up afterwards. So that dry ice that goes from solid to a gas is sublimation. If I want to go to a gas back down to a solid, this is a word most people never heard of, deposition. So what we're doing is we're depositing solid, okay, from a gas. And now let's talk about our two types of vaporization. Vaporization is when we go from a liquid to a gas, and I want you to get used to these symbols. Okay, so we have boiling, and we have evaporation. So boiling is when the atmospheric pressure equals the vapor pressure. Let's say it backwards. Vapor pressure above a liquid. So that's right when our little liquid is turning into vapor. So vapor pressure above the liquid equals or is greater than atmospheric pressure. And we're going to do more on this. Evaporation is when we have particles with enough kinetic energy that can escape that liquid. So here we have, let's go back here. So when we're boiling, we have this vapor pressure. That's the pressure of the gas right above the liquid pushing up. And then we have atmospheric pressure pushing down. If this is much smaller than that, we do have some going from a liquid to a gas, and that's evaporation. If these two arrows become equal, then we have boiling. So evaporation is when some particles have enough energy to escape the liquid and turn into gas. Okay, so if I have enough energy in some of these particles, they can go to a gas, and slowly over time they will start evaporating. Boiling is when there's so much turning into gas so fast that it can overcome this atmospheric pressure keeping the water together, and that's what we call boiling. And again, we'll go through that in more detail later.